chapter 6, we're going to talk about the sequence data and sequence processing. So we start with recurrent neural networks. It's a bit old-fashioned, but you really enjoy knowing it because it's going to give you a clear idea of extracting context from sequence data. And then we are not going to do too much on this chapter. So it is actually longer than the other chapters. But the last part I'm going to skip. I'm going to give you the overview what CTC is. But since it's not that practical anymore, I just leave it for you. I have the recorded video, so I can share it with you if you want to just know the details. It's interesting mathematically, but less important nowadays, because nowadays we mostly work with transformer. But the things that you have studied up to this point are simply FNN, right? So you have your data. You have, for example, a label for it. The data goes in. The output comes out. That's it, right? There is nothing else, right? The next data that you see is dependent of what you have seen before, right? One image is independent of the other image. This is the most basic thing that you can work with neural networks, or say computational models with. But in practice, we usually have sequence data. And sequence data are the ones which have made all the progress in AI nowadays. They are data which have some sort of temporal connection among the components, right? So a text is a temporal, is a sequence data, right? Every single word in a sentence somehow relates to the other words inside the sentence, right? Or, for instance, thinking about a video, it's again a temporal sequence, right? Because you have every single frame which is somehow related to the previous frame, right? It cannot be totally different. So sequence data are actually the main things you see in most applications nowadays. Speech data is one of them. Text data, financial data even, is a sort of sequence data, right? You do not, I mean, it happens that the gold price just suddenly goes up, right? Some office gets closed, and then this goes up, right? But it comes down. And then there is usually a sort of smoothness inside the data. You don't expect seeing the price of something today 1 and then tomorrow 10,000, right? So everything that you see in practice is usually sequence data. Even the data that we have worked up to this point, you can think of them as sequence data, but they are so simple that we can just ignore that fact of being sequence, right? And the thing that you do is that usually if you want to learn by the feed-forward neural networks that you have, basically MLP, CNN, ResNet, whatever you learned up to this point, if you want to try to use it, then you're going to get into a quite big trouble. So you're going to see that you need to have a giant network to do the job for you. And that giant network is obviously unnecessary. Like the complication you see inside that network is unnecessary. And it's not scalable, it's not sustainable. You cannot scale it up to the extent that you want. So one key point here that you might see is that typically when you deal with sequence data, you usually need to just get a very specific context out of that sequence data, which is not that big, right? When I'm speaking to you and I keep on talking, then at some point you probably can guess what's going to be the next word I'm going to say, right? Or you roughly have an idea. And you don't really do anything complicated, right? You simply listen to my whole sequence of words, and then you do not even remember them, right? But something in your mind keeps the context, right? And you expect that the next word I'm going to say is something about neural network, right? You don't expect me to talk about art right now, right? And this is simply because you see I am talking about, this lecture is about deep learning. I am talking about neural networks. So usually the things that you want is not that complicated, but the key point is that well, the point is that if we want to just do it with vanilla feed-forward neural network, this is not really a good idea. So what we're going to do, we're going to try to develop some better solutions, which are basically sequence models. Now, sequence models, the most basic one is recurrent neural networks, which you can built using your own neural network. Like you get any neural network that we had up to this point, and then you just build a recursion inside it, and this is going to be recurrent neural networks. Most famous ones are LSTM and GRU, which we're going to talk. They're using gating to somehow handle some computational issues, but you can basically do it with any neural network. Then, later on, we're going to get into transformers in the next chapter, and transformers are actually the trend nowadays. They are the one which do, again, process sequence data, but they do it more efficiently. Now, let's just start with the sequence data. Just to give you a bit of idea what kind of problem you should think of when you want to visualize the problem for yourself. One of the things is just, for example, speech processing. So say I have one 15-minute talk, so you listen to that talk. This is either about sport or science, okay? So this is a talk. The topic is either sport and science. What you want to do, you want to just take that file, give it into an algorithm, a neural network, something, and that algorithm, that machine, going to give you this classification label, whether it's about science or sport, right? And this is basically a classification problem, right? Your data is the 15-minute stock, and your label is just binary, right? Science or sport, right? So you can think of a classic neural network, right? You can say, OK, I have an MLP, and then this MLP going to take 15 minutes talk, that giant talk. It's going to take it, process it, and going to give me the label 0 or 1, right? 0 is sport, 1 is science, right? Now, how does the data look like, the data that you want to give to your MLP? Well, it's going to look like this, right? So I'm not sure if everybody has this signal processing background, but I try to explain it. I think everybody who works with computer knows a bit about how you store speech on your computer. When you have a speech on your computer, how do you store it? Do you have any idea? Yes? You sample it, right? So if you have the true speech that I'm talking is actually a continuous signal, right? So it's an acoustic signal, just you get the microphone, you're going to vibrate. Out of that vibration, you're going to see. This is how it looks like, right? This is when I pick up, right? Back propagation, and then again, right? This is just the amplitude, right? And then there is a frequency inside that which depends on the tones inside my voice, right? So some tones are like high frequency, it's going to just vibrate faster. Some of them are low frequency, so vibrate. So this is your sequence, but this is your speech, but of course you cannot save it like this on your computer. What you do, you're going to sample it, right? And then there is Nyquist theorem. If you sample enough fast, then you're going to be able to recover it, right? And based on this theorem, you can simply get this audio, which is a continuous signal, and save it, just the samples of it, right? So it means that it's going to be every single point that you see here is just compressed too much, but it's a kind of like time 1, 2, sampling time 1, 2, 3, and so on, right? And every single of them is just one number, right? Some number between minus largest one to plus largest one, right? Now, these are samples. You usually have a frequency for your sampling. Like this is a classic frequency for sampling, 44.1 kilohertz. It means that 44,100 samples you take per second, right? 1 second of audio going to have that much samples inside it, 44,100, right? So this is the amount of samples you have in 1 second. You typically quantize it because you have limited precision on your computer, but we can ignore it because our computers are good nowadays. And then what you do, you usually put them inside frames, right? So it means that you have this audio. It might be 15 minutes. 15 times 60 is going to be the number of seconds you have, right? Times 44,100 is the number of samples you have. It's giant, right? It's huge. So you typically don't work with them directly, completely. So what you do, you keep frames. Like you would say, OK, I'm going to save every single 10 seconds into one frame, right? So you usually have frames of size n. So this is the first frame. It's including a bunch of samples, right? This is the second frame, the next n samples, and so on, right? And you typically show your sequence like this, right? So what is every single x? Can you tell me? What kind of mathematical object is it? It's a vector. How many entries does it have? the frame size, right? N different samples, we said, in every frame. So it has n vector of size n, right? So this vector of size n is your audio for a short period of time, right? And then you have the sequence. This is the kind of data that you have, right? And then what you want to just give this whole data and then find out what is the topic of this speech. Everybody's clear, right? Now, sometimes people might do more, like maybe they take the Fourier transform of this. I hope that you know what it is, but if you don't know, you just get the signal in time domain. You just do a mathematical operation on it, then you get its equivalent in the frequency domain. And again, you can sample in the frequency domain and save it in the frequency domain, right? And then you have the time domain and frequency domain signal, right? Now, you can have it as well, like x1 you have, for example, is FFT, right? X or XF1, or I don't know, whatever you call it, right? So every single body could have its own frequency domain as well. But at the end of the day, every single entry you see here itself is a big vector, right? Everybody's cool about that, right? Now, that's one case. And now let's say that you want to just do classification. So the data here is indeed a sequence data. The reason that it's sequence is because, first of all, like x2, it's really depending on x1, right? Because probably the thing that you're talking about is going to continue over seconds, right? And every single part of your audio is having a part of your speech, right? So you cannot say that x2 is totally independent of x1 anymore, right? So here, this guy has a very good correlation with this one, whereas this is not the case when you have images, right? So this is sequence data, a sequence of vectors. If you want to know, for example, the size of, just to know a sample, just get a bit of sensing about the values. So if you have 15 minutes talk, then you typically do frames in power of 2, so 512 samples inside a frame is quite a typical thing. And then if you just consider how many samples you have in 15 minutes talk, basically you have around 80,000 frames for 15 minutes talk, which is equivalent to like 40 million samples, right? And now, if you want to get this 15 minutes talk and directly classify it out of the sample, this means that you have a neural network with 40 million inputs, right? And then only one binary output, right? This is not going to work, right? So it's not only about, it does not seem to be really working. And it's not only about the fact that 15 minutes is too long, right? I mean, the point is that at the end of the day, you need to have something sustainable, right? What if the speech is now next time 20 minutes, right? What if the speaker is this guy who is talking forever, right? So this is going to be longer, and then you need to have some algorithm which works with any talk, right? So this is not really sustainable anymore. But one thing that you might guess here is that this is not really necessary to know all those samples in order to find out what is this talk about, right? Like if you want to know whether it's about science or sport, probably just some keywords, some buzzwords gonna make it, right? So it's talking about soccer and basketball and tennis, so it's about a sport, right? It's talking about, I don't know, quantum physics, chemistry, earthquakes, so it's probably about science, right? So just some buzzwords going to do the job, but you need to be able to extract those buzzwords, right? To somehow get the idea of what are those buzzwords about, right? So this is the issue. So typically you have some simple words in these expressions that you can simply find out what is this talk about, but you need to be able to get them, right? Somehow you need a way to store them, right? Inside sort of memory, right? Everybody's clear? So this is one example that you might have. So as I told you, the vanilla approach is not going to be really practical. It seems very large if you want to work with this one, so computation is very hard, and you cannot generalize simply because if the talk is very longer or very shorter, then your neural network needs essentially to change the number of inputs, right? It's not going to work. So this is one thing. One other example is about predicting the next word in the sentence. So this is, again, one typical application. Nowadays, we have it. All of us have it on our cell phones, right? When you're texting, typically you have a sentence, and then that sentence is, so let me show it, is some sentence like this: UofT undergraduate, so on, to treat SP, you type SP, and then it just offers you some options, right? Speech or sport, right? It's going to give you different options, right? And now, what is this kind of problem? This problem is, again, a classic problem we have in neural networks, right? This is a prediction problem, right? But this prediction problem that you see here is essentially, again, a classification problem. Do you know why this is a classification problem? We're going to talk about it in the next chapters quite a lot, so you're going to get it roughly clear why this is a classification problem. But can you see here, like, you see all of this sequence, right? And I'm going to explain it, how this sequence is, right? Or maybe I should explain it first. So if you want to get this text and you want to put it inside in the form of this sequence, how do you do this? Well, every single letter here is on your computer is a part of your memory, right? And you save it on your computer by some sort of encoding, right? So you have the letters. Maybe you use, I don't know, ASCII codes, right? Old-fashioned. You get the word, you just take the ASCII code, you save it on your computer, right? Your computer understands it based on that. This means that every single letter here is an ASCII code, right? And then this whole text is a sequence of digits, right? And then what you do, you just pack every couple of letters, or every couple of what we call them tokens later. So you're going to pack every couple of them together. This is going to be one vector, right? X1 is maybe therapy, right? And this therapy is shown because it is, I don't know, 1, 2, 3, 4, 5, 6, 7 words, 7 letters. Then it's shown with a specific size, right? And then you're going to collect the next 7 letters or 7 symbols together, and so on, right? So every single of them is showing one part of this text. But obviously, again, this sequence, every single guy here is depending on the others. Agreed? Because if, for example, x2 is UofT und UND, right? Then the next one, x3, is going to be R undergraduate, right? And then ER graduate is going to depend on this fact that the previous one included und, right? Undergraduate. You don't have undor graduate, for example, as a word, right? So obviously, when you know this x2, you probably can talk about x3, and this means that they are correlated, right? Now, sorry. If you come up here and you get into this word, now your computer wants to just guess the next, say, for example, 7 letters, right? And again, this is a classification problem. Why? Because what can it be the 7 letters, right? Every letter on your computer is at most something, right? So maybe you have, I don't know, 30, 80, 100 different symbols for as a letter, right? Like the English letters plus digits plus space plus all marks, question marks, and other things. You put all of them together, there is at the end one specific number of possible letters, right? Possible symbols, indices on your computer, right? You want to pack 7 of them together. So it's going to be, say, if you have 100, this is going to be 100 to power 7 possible cases, right? So among these 107 possible cases, you want to just choose one of them, right? And this is, again, classification, right? Very giant classification, but still a classification, right? So this is, again, a classification problem. But obviously, when you want to put this speech here, right, you do not simply look at SP here, right? Because this speech could be sport as well, right? But why this is speech? Maybe because this is use of AI. Maybe AI is talking about this. There are some undergraduate students here, so probably it's a speech, not a sport, right? Your brain somehow guessed that this is a speech more than a sport simply because it looks at everything inside the text. Maybe you even need to look at the previous words, like therapy is talking a lot about that one, right? So it's, again, a kind of problem working with sequence. Your sequence could be very large, And then what you want to do, you want to do simple task that is a classification task, but you need to do it based on the information inside the whole text. And we can say, again, the same story as before, because here you would say, well, if I want to classify this guy, I don't need to know every single letter in the whole text, right? I just know what is this text about, right? Just a finite amount of information about that text, a bit of context to that text. And then out of that, I want to just classify my next word, right? So, same thing, you can talk about like financial data. For example, you have the previous trend, right? You have all the data of, I don't know, one specific stock price, and then what you want to predict is what is the next price, right? This is a kind of regression problem, right? It's a prediction, but in the regression form, because you want to, for example, estimate the next price or predict the price, which is a real value label. And then what you have a sequence of data, right? All the prices before, from very beginning of the stock being in the market till now. And all the soft information, like what happened globally about gold, what happened to the US government, what happened to the Canadian government. You need all of this information, right? And these are going to impact as well. If you can fit them into your algorithm, this is going to get a better prediction. So again, you are dealing with a sequence of data. And this problem, again, could be very challenging if you want to do it basically by an FNN, right? If you want to simply give all the information and feed it into a 154 neural network, this is not practical. Okay, so what we see here is that we basically need a kind of memory in these problems when we deal with sequences. So a kind of memory that is looking at the whole sequence and extracting a sort of context out of that sequence, right? Something that is explaining what this sequence is about, right? Now, this memory is, theoretically, it needs to be infinite in time. What does it mean? It means that if my text is as long as 10 bucks, I should still be able to go back and get the context, right? If there is one important word somewhere in page 1, and I'm now in page 1032, I should be able to know about that, right? So it should go infinite in time. But what about its size? Should the size be infinite as well? Do you have infinite size in your brain for memory? No. I mean, we cannot memorize every details, right? But our brain somehow gets the context, right? You just get into interaction with other people, and through that, you remember some specific things, right? Why you remember them? Because they are going to help you interact, right? You don't need to know every details of other people's life, but as long as you do know like what happened last year to that guy, you still are able to interact, right? So the key point here is that it does not really need to be infinitely large, right, in size. So it should be limited in storage, but it should be infinite in time, right? You should just capture anything in time, but you practically need finite size, right? And this is a kind of memory component we are missing in the basic neural networks that we have. Now, let me just start with this particular example. Then with this example, we try first MLP, CNN, see why we cannot actually use them directly to accomplish this task. And then we see how we can resolve that issue. So what is the problem here? So this is the problem of predicting the next word. And this example, actually, I thought a lot about this to make it. And then we're going to have it for maybe even I think all of this chapter. So this is going to help quite a lot. So we have this sentence. So it says, Julia has been nominated to receive Alexander von Humboldt Prize for the next word, right? Now, if I don't show you the next word, what do you say? If you know that this is going to be a pronoun, what do you put? What do you put if you know that this is a pronoun? Her, right? Why you put her? Because of Julia, right? Julia is a female, you put her, right? So Did you care about anything here in between? Did you care about Alexander von Humboldt? No, right? Did you care about nominated? No, right? So you read this text. If I tell you what was the text, tell me exactly. You probably cannot say it exactly word by word, right? But you know that you should put her, right? Because Julia is typically a female, right? And I should put her, right? So this is the problem that we want to do. So we don't know the next word. We want to build a machine which is able to predict the next word, right? And then this machine is potentially having access to the whole sentence, right? Or even before, right? We can't give whatever it wants, right? But we need to make it feasible. Like, we need to do it practically possible way. So, one thing, if you want to just do a very basic approach, the basic approach is that we give the whole sequence, right? The whole text, whatever we have, into the neural network. We say that just try to process it and then tell me what is the next word, right? So how I can do it, let's start building some neural networks. Say that I have this particular neural network. I'm going to use this diagram quite a lot in this chapter, and I'm going to explain what it is. So let's make it clear. So this diagram is somehow the compact version of the FNNs that we have, MLP or CNN that we had, right? So here we have one input layer, right? This X could be giant, right? This is the whole input. So it could be a vector. It could be an image, right? It's the input to a CNN, right? Anything. Now, now you do know that anything could go inside a neural network, right? Now, here is a hidden layer, right? Or a bunch of hidden layers in practice. So it could be multiple fully connected layers. It could be multiple convolutional layers, right? And this very output is the last layer, the output layer, right? Which is giving you your label. Everybody's clear? So this guy, the green box, is the input layer. Yellow box includes all the hidden layers that you have inside your neural network. And this is just simply an FNN, right? It could be convolutional. It could be fully connected, whatever. And then the red box is basically the output layer. This is going to help us more when we are just dealing with sequences, because you don't want to have all the neurons shown here, right? And you don't need it anymore. You do know how this works, right? So, and the arrows basically include all the connections inside your neural network, obviously. So, for example, you might think of it like this, right? So you have a bunch of inputs. It goes to the first layer, right? Hidden layer. It gets computed. It computes a bunch of outputs and then again processed with the next hidden layer and then gets to the output layer, right? This could be, for example, one example, right? Or you can put those yellow neurons, you can replace them by convolutional layers, right? Okay. So now what we want to do, we want to just get this guy, so you can think of it, as I told you, as an MLP, and then we want to just train it in a way that this is able to go over the text, right, and then tells us what is the next word, right? And let's try to do it with our sequence. So this guy comes here, right? And this neural network going to take the first entry inside the sequence as the input, right? Okay? Everybody's cool? Now, if I want to make this neural network to be able to predict the next word, what do you suggest that I consider as the label? So Julia is the word going in, right? What do you think would be the next word to come out? And right now, think simply, right? Assume that every single word in this sentence is one single vector. So every X here is one of the words inside the sentence. What do you put if you give Julia as the input to this neural network and you are training it? What do you put as the label for Julia? What is the next word to Julia? Has, or maybe has been together, right? So I give Julia to the network, and then I just train it. I just find the weights, fine-tune the weights. I just do some steps of gradient descent to just make the output looks like the label has or has been, right? Correct? Okay, say I do this training, then I go for the next time. Next time I'm getting has been as input. What do I put as the next word? Nominated. So I just, again, train this guy, tune the weights inside this neural network so that when it sees has been, it's going to give me as the output nominated, right? I go next, I give nominated, I just do gradient descent so that the output looks like to receive, right? Everybody's cool, right? You see what I'm doing, yeah? You have any confusion? Yes?
About the size, usually the inputs are all the same size?
Yes, typically.
In this case, if you want to put like a full label that means something, that means will the inputs be of different size?
No. We're going to talk about this. We're going to do tokenization in practice. So this means that you look at a sentence, or you look at a large corpus of text, and then you learn what are the tokens, what are the components of this text, right? So there are one basic components of the sentence, and once you label them, then any text could be represented as a sequence of indices, right? And then everybody is represented by one embedding, and that embedding is just same size, right? But for now, what you can think easily, you can think that like you have a word, you just consider a maximum size for a word, right? And then you represent Yulia to be Yulia, and a space, a space, a space towards the end, right? And then has been is another word, whatever left is just empty, right? And so on. You can do this. This is the most dummy way of tokenization, right? But we have better approaches for tokenization. We talk about that. Okay. Everybody's cool what we're doing, right? So we are just bringing this neural network every time, and every time that we bring it forward, we give the word that we have into the neural network, and we make it to just give us the next word as the output, right? Now, let's say that we have done it up to this point, right? And we go for the next time. Now, here is the last part. So, for example, price for goes inside the neural network. And now, this is the time that we want to do inference with our neural network. So we have done the training over the whole text. Probably we did not start simply from Yulia. We started long, long before in the text, and we did all the training. Now is the time that we need to exploit it. Do you think that if I give to this guy price for, this is able to give her as the output? Do you think that is going to happen? Yes or no? No. Why you think it's no? Because saying her is not only depending on price for, right? Maybe if we have done it on a very, very long text, it has seen that after for, it should always bring a noun, right? And it's going to suggest a noun after for, right? After proposition for, it's going to give you a noun. But what noun should it come, right? Should it be a pronoun? Should it be a simple noun? Should it be a verb plus ing? It does not know, right? And there is no reason for it to find out like her is better than anything else. We do know it because we know Yulia is here, right? And we know we're talking about her, right? So this is probably her, right? But we cannot do it right now. We cannot. The neural network cannot guess it, right? So obviously, this is not able to guess that this is her because this cannot remember anything about Yulia, right? For it, Yulia was just one input, right? And its corresponding output was has been, right? That's it, right? So the only thing that it captured maybe was that when Yulia is coming in, you should talk about single person, right? That's it, right? Third party single person. That's it. So it cannot do it. Now the question is that how we can. Let's first of all see the pattern here. So the pattern here is that every time that we go over the sequence, the neural network somehow learns to give the next word given the previous word, right? And then, or given the current word, right? And then it only somehow learns a superposition of all of the connections between every single word in the sequence and the next one, right? So there are some immediate connections between them, like when you have a first person, third party, then it's going to be the next one is going to be like a specific, like the verb is conjugated some specific way. If it is a pronoun, like a preposition, then it's going to be a noun. Maybe it captures some immediate connections like that, but rather than that, it's unable to just capture the long-term information inside the text, right? Obviously, this is not able to do it. And when it gets to time t, the only thing that it has as the information is the last word coming inside the neural network. It already has forgotten everything about Julia, right? Julia plays no role in its decision when it wants to give the next word after 4, right? So this is the key point, and this is what I told you. So we are missing some sort of memory component, right? So we do not have memory component. The neural network cannot find out, cannot remember what was the whole text about, right? It was about a third-party female who won a prize, right? It cannot remember that, right? Okay, so now, how can we resolve that issue? Well, maybe very easy idea. Maybe we can make the input so large somehow that Julia somehow can get in, right? So it means that I have this giant network, right? And this giant network is going to take everything from this point of time to here, right? And then it's going to tell me what is the next word. Now, if I train this guy over a very, very, very large text, so we usually say a corpus. Corpus means like you go on internet, you scrape everything on internet, you just put it in form of a text. This is a huge, giant amount of data, right? Tons of data, right? And then you put all of them as a text next to each other. So it's about everything, right? Whatever you find online. And then you train your neural network on that. This is how, for example, LLMs are getting trained. And when you do that, then, well, yeah, maybe it can tell you that it's her because Julia is somehow getting in, right? But what if, for example, Julia was happening 10 pages ago, right? So you're somehow happened that you don't bring the name anymore, right? But you keep talking about her, right? You, as an intelligent creature, gonna get it at that point, right? And you don't have infinite size memory. I mean, we have a big memory, of course, but we don't have infinite size memory, right? We'll only capture this fact that this text is about that person, right? So this does not sound to be really practical. This is why we cannot simply use MLP for this task. Just forget about it. This is impossible. But you might tell me that, okay, maybe we can use the idea of convolution, right? Just let's do one-dimensional convolution. Scroll over the text. This might be helpful, right? Because this is going to somehow, through convolution, which has less complexity, going to capture information of the whole sequence, right? Well, that makes sense, so maybe I just do it by a convolution. So what do? I'm going to make a filter which is of size n, right? And this size n is exactly the size of one single vector in my sequence, right? Every single xt in that sequence is of size n. Then I get this guy, and then I scroll it over time, right? So I would say this was the multiplication to the first entry. Then I go next time, I sum them up. And then this is the convolution. The whole input goes inside my neural network. Again, gets processed with this layer, and then it gives me the output. Everybody's cool? Questions? So you got how I'm doing it, right? So if I do that, then what does it mean? It means that, for example, when I am at this particular time, and I want to predict the next word here, right? So nominated, for example. I have this filter. It starts to get multiplied with two time instances before, then one time instance before, and then exactly that time. And then sum up all the convolutions, right? All the multiplications, and then give it as the input to my neural network, right? Now, this guy is obviously at this time when it's talking about the next word and nominated, it's looking into the words Julia and has been, right? Everybody's clear? So it's looking into those words, and then it's just giving the next word prediction, right? Just a second. Something jumped. Sorry. So, this guy is now, when he's talking about the next word, is just looking into the whole sequence, right? To the whole 3 words before, right? And if you go over time, like the next time, when he wants to talk about Alexander, he is just looking into to receive, nominated, has been, and so on, right? If you bring this guy here and you want to predict the next word, do you think that it's going to be able to just tell you her? It's still not able, right? Because when it's going to talk about her, it's going to just look at the last 3 words, right? What if I want to just make Julia in, right? Just let it in. I should expand my whole convolution, right, size. So I should just expand this filter to go all the way back to Julia, right? Well, this is less complexity as compared to FNN, the MLP that we had. But obviously, this is not, again, generalizing, right? Because if Julia has happened long time ago, then I need, every time that I want to predict the next word, I need to start from very beginning word in the whole text that I have, and I go over all of it till my current word, and then I just predict my next word, right? If I'm doing it over a giant text, then forget about it again, right? So this is, again, not very feasible. So the problem that you see here is that all of these architectures that we have, MLP and CNN, all of them, they have a sort of limited size in time, limited time, finite in time, memory, right? So they can capture within a sequence a finite amount of time, right? And it makes sense because they are actually not built to work with sequences. They are built to just look at the whole data at once and talk about it, right? And if you want to give a sequence, you need to add one extra component. So they can remember whatever is inside their input. When they get into a new input, they'll look at that input totally independent of the other one, right? And this is how we thought at the very beginning. So every single image that we give into a convolutional neural network, we think of it to be one independent image, right? This is image of one cat. This is image of another cat, right? But this is not suitable for these sequences, right? So if we want to really work with sequences, we need to somehow have a way to extract a sort of long time, or theoretically infinite in time, memory over a very huge input. But the key point here is that the memory component does not need to be very huge, right? When you want to just talk about the next word, you really don't need to remember every single word inside the entire text, right? You only need to know what is this text about, right? And then probably you are able to give a better prediction for the next word, right? So this is the key point here. You don't need infinite in size, so this does not need to be huge, but this should somehow carry information quite constantly over time, right? And this information should somehow be able to somehow extract the essence of that sequence, right? For example, if you had in the text, you're talking about Julia, and at some point the text starts to stop talking about Julia, just changes to someone else, right? Theodore in my example. Then it should be able to just change from her to his, right? Because it's a single person, third person male, so I should change to that particular pronoun, right? Everybody's clear? So do you see what we are missing right now? So we computationally are able to process things, like we are able to process every single entry inside this sequence. That we can do, but the only issue is that we are somehow not capturing the temporal connections between them. And to do that, we need a sort of memory, right? Okay. So the component we are missing is a sort of memory component. That memory component should be finite in size, but it should somehow get influenced infinitely in time, right? So if a word is changing somewhere at the very beginning of the text, or memory should change, but the size of that memory doesn't really need to be infinite, right? And do you have any idea how we can do it? Those of you who had like EE background or mechanical engineering background, probably you have some idea, yes? At a feedback loop, that is possible, but when you do feedback loop, what do you add to your system? Well, it's a memory, that's right, but what do you call that memory? I guess what is it? State, right. You add a state to your system, right? So you might have seen it in other courses. So when you have a system, which you want to capture the temporal state of the whole sequence, right? You add what you call it a state, right? You would say that this system is getting one input and giving me one output, but every time it's going to look at something else, which is finite in size, right? And that is a state. And that state is telling my system in which operation situation you are, right? So probably that is going to work here as well, right? And this is what we are going to do. We are going to add a state into our model. And that state is essentially the context we are looking for, right? So we want to add some state, which is grasping the context of the sequence. We'll somehow save that context inside that state. And every time that we want to decide for the future, we decide based on the input plus the state, right? Plus the context. So state and space models are going to just give us that context that we want. How do they look like? So they usually look like this. So in addition to the input xt that is going to your system, and the output yt that is coming out of the system, exactly what we have one extra variable which is called state, right? And that state is getting updated every single time. So typically we do it this way. So every single time that the new input goes in, that new input, along with the current state of your system, is going to decide what is the output of your system and what is the next state. So you're going to update this state as well, right? So it's like a memory, extra memory you have in your system. You look at the input, you look at the state, and you're going to say, OK, this is the output, and then you change your state, right? Every single time, right? So this is a very general form of a state space model, right? And the thing we want to do, we want to build such a model using a neural network, right? We somehow want to incorporate that state into our neural network. Everybody's clear? Questions? Right? So this guy, this state, is somehow able to carry information infinitely long in time, because you can say that, like, if you really want to have Julia in your memory left, right? When you get to Julia, you can just put your state to be Julia, right? And then you don't change it forever, right? Every time that you are giving output, you look at Julia, the new input, you give your output, right? Julia theoretically can just carry all the time, right? Infinite over time, right? Unless you really decide to change it, right? Maybe your memory is sensitive to the name of people, right? And it's going to just keep Julia forever unless you start talking about someone else, right? This is one choice. So theoretically, state could somehow carry information infinite over time. And we can actually see it simply inside a neural network. So